Hi folks, Astronomy Live here. For the past couple of weeks I've tracked asteroid 1998 OR2, which is set to make a close approach to Earth on April 29th. You can see it here in time-lapse videos recorded on April 12th and April 18th. Various tabloid sources have made doomsday claims about this asteroid, including an article published by The Express last year, which suggested that NASA could not rule out the possibility of an impact occurring with Earth this month. It even suggested that NASA's administrator could not rule out the possibility of an impact. Let's see what we can do to figure out if this asteroid is a potential threat for impact or not. The first step in this process is to measure and log the coordinates of the asteroid over time in order to calculate the orbit. This is called astrometry. I modified my Comet Astrometry program to now handle asteroids, which have a slightly different naming convention. I also changed it to target the midpoint of the streak and the midpoint of the exposure, and to handle both color and grayscale images. You'll find a link to the source code in the video description. Once the asteroid's position has been measured over time, the resulting output file can then be loaded into FindOrb to solve for the orbit. You can see my solution for the orbit of the asteroid on the right. The observing station has been picked to be reasonably close to my observing location without giving away my exact location. The resulting orbital solution will be published in the link in the video description as well. Now in the center we can see what my orbital solution predicts to be the close approach distance between the asteroid and Earth, 0.042 astronomical units, which translates to about 16.4 times the distance to the Moon. This is, however, just a nominal solution for the orbit. It doesn't actually tell us how certain our orbital solution is, and whether or not an impact is truly possible. To know that, we need to look at the orbital uncertainty. There's a little bit of uncertainty with each astrometric measurement, especially since OpenCV was used to automatically target the middle of the streak. So by adding a little bit of random noise to each observation and then solving for the orbit many times, we end up with a series of orbital solutions that all fit closely with the data and tell us how certain our orbital determination really is. At the end of this process, we now have virtual asteroids that represent solutions that are very close to our observational data, but we need a way of visualizing them, and ideally we need a way of integrating their orbits over time while also accounting for the influence of the gravity of the planets on the trajectories. As you might have guessed, my solution is to write another program in Python, this time using Rebound to perform solar system integrations that account for the gravity of the planets. It also allows me to easily plot the trajectories of these virtual asteroids through the solar system and see if any of them intersect with Earth. Unlike most of my programs, this one will not run in Windows. Rebound requires Linux, and that's fine with me. I do have Linux on my machine. But I'm not quite done writing this yet. It's functional for the purposes of this video, but it's not an elegant solution, and I would like to add some more features to it before distributing it. However, if you're really interested in the ongoing progress of my work, I'll be happy to send you the source code. Finally, here's the plot of the integration. The orbit on the right, which is highly elliptical, represents the orbits of all of the Monte Carlo solutions. They form a very tight point that you can see in the black dot. It's almost just as tight as the planets themselves. Its position is known very well, even just based on my observations alone, and as you can see, that point does not intersect Earth's point, which is moving around in the purple line just inside of the asteroid's orbit. What this means is there really is no risk to Earth from this asteroid on this orbit. It will stay about 16 times the distance to the Moon away from Earth at its closest point. I will include the link to my Astrometry software in the video description. If you want the asteroid integrator that was used to generate these plots, feel free to drop me a comment and I'll be happy to send you the work in progress. I'll also include a link to all of my astrometry and orbit data on this asteroid so you can verify my calculations for yourself if you desire. Until next time, clear skies, folks.